Hello. Welcome to this lesson Diode Models. A practical diode has a nonlinear voltage current characteristic. Analyzing every circuit using the exact exponential diode equation can be difficult and time-consuming. Therefore, engineers replace the real diode with an approximate equivalent model. In this lesson, we will study three commonly used diode models: the ideal model, the simplified model, and the piecewise linear model. Each successive model gives a more realistic representation of diode behavior. Let us begin with the ideal equivalent model. In this model, the practical diode is replaced by an ideal diode. The voltage across the diode is represented by Vd, and the diode current is represented by Id. When the ideal diode is forward biased, it conducts perfectly. It behaves like a closed switch or a short circuit. Therefore, the voltage drop across a forward biased ideal diode is zero. In other words, during forward conduction, Vd is equal to 0 volts. Now observe the ideal diode characteristic. In reverse bias, the current is zero. The diode behaves like an open switch and is assumed to have infinite resistance. In forward bias, the diode can carry current and the voltage across it remains zero. This is represented by the vertical line along the current axis. The ideal diode therefore has two simple operating conditions. In forward bias, it is a short circuit. In reverse bias, it is an open circuit. This model assumes zero forward voltage drop, infinite reverse resistance, and conduction in only one direction. The ideal model is useful when the diode voltage drop is very small compared with the other voltages in the circuit. For example, in a rectifier supplied by a relatively large voltage, ignoring the diode drop may provide a quick and sufficiently accurate first approximation. However, a real silicon diode does not begin conducting at 0 volts. To account for this limitation, we use the simplified equivalent model. The simplified model includes the forward voltage drop of the diode but ignores its internal series resistance. A silicon diode is represented by an ideal diode connected in series with a fixed voltage source. This voltage is called the knee voltage or threshold voltage, represented by Vk. For a silicon diode, Vk is approximately 0.7 volts. The polarity of this voltage source opposes the applied forward voltage. Therefore, the external voltage must first overcome this 0.7 volt barrier before the ideal diode can conduct. Now consider the characteristic curve. In reverse bias, the diode blocks current, just as in the ideal model. Therefore, the reverse current is assumed to be zero. During forward bias, the current remains zero until Vd reaches the knee voltage. Once Vd becomes equal to or greater than Vk, the diode begins to conduct. For a silicon diode, conduction therefore begins at approximately 0.7 volts. After this point, the diode voltage is assumed to remain fixed at 0.7 volts, irrespective of the current. The simplified model therefore includes a fixed forward voltage drop but assumes zero series resistance. This model is widely used in general direct current circuit analysis. It is particularly useful when the 0.7 volt diode drop is significant compared with the supply voltage. For example, in a low-voltage rectifier, ignoring the diode drop may produce a noticeable error in the calculated output voltage. In such cases, the simplified model gives a better estimate than the ideal model. We now move to the piecewise linear equivalent model. This is the most accurate of the three approximate models. Like the simplified model, it includes the knee voltage Vk, which is approximately 0.7 volts for a silicon diode. In addition, it includes a series resistance represented by R sub AV, or the average forward resistance. The diode is therefore modeled using a fixed voltage source and a series resistance. In reverse bias, the diode is still treated as an open circuit, and the reverse current is assumed to be zero. In forward bias, conduction begins only after the applied voltage reaches the knee voltage. Beyond this point, the current increases as the diode voltage increases. Unlike the simplified model, the forward voltage is no longer assumed to remain exactly constant. A portion of the diode voltage appears across the series resistance. The forward diode voltage may therefore be written as the knee voltage plus the voltage drop across the average resistance. The forward characteristic is represented by a sloping straight line. The slope of this line is equal to 1 divided by R sub AV. From the graph, the average resistance can be estimated using the change in voltage divided by the corresponding change in current. A smaller resistance produces a steeper characteristic, while a larger resistance produces a less steep characteristic. The piecewise linear model is useful when greater precision is required, particularly when the current through the diode changes over a wide range. Let us now compare the three models. The ideal model assumes no forward voltage drop and no forward resistance. It is the simplest model. The simplified model includes the approximately 0.7 volt forward drop of a silicon diode but ignores series resistance. The piecewise linear model includes both the forward threshold voltage and the effect of the diode's average forward resistance. These models will be very useful when we analyze diode rectifiers. In the ideal model, the entire input voltage may appear across the load during conduction. In the simplified model, approximately 0.7 volts must be subtracted for each conducting silicon diode. In a bridge rectifier, two diodes conduct during each half cycle, so the total approximate diode drop becomes 1.4 volts. The main takeaway is that diode equivalent models simplify circuit analysis by approximating the behavior of a real diode. The appropriate model should be selected according to the required accuracy and the application.